Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we talked about Doppler effect. Do you remember what it was, or do you remember the equation? I hope you do so. So we said basically when there was a relative motion or where there was a relative approach between the two objects, whether it is, let's say, the source and the observer, of course, we'll hear a frequency that is higher than the frequency of the source, let's say. But if these two are moving away from one another, of course, the frequency that we are hearing basically is going to be lower or less than the frequency of the source. All right, very good. Or you can say, of course, the pitch that we're hearing is going to be higher in terms of approaching, and of course, if they're moving away or moving apart from one another, the pitch will be lower than the pitch of the source. All right, so today we'll talk about section 4.2, and that is, of course, sound intensity and resonance. So let's talk about sound first. All right. Now remember this. Okay. So previously we said, or in the other sections, of course, or in the other video lessons, we said the audible frequency that, or let's say the audible range for a human, it varies between, let's say, or lies between 20 hertz to 20,000 hertz, yeah? But that is not the only thing, of course, that affects the audibility of human hearing. Of course, there is another factor that is related to that, and that is intensity, or you can say wave intensity. What do I mean by this? Imagine, let's say we are in, let's say, in a hall or something, yeah? Or in a very big room, let's say, or let's just say that we are in a stadium and two friends are very close and talking, and of course there is another friend that is far from them, yeah? When you are talking normally between you two together, of course the other person is not hearing you, even though the frequency, for example, that your sound, of course, it is in the audible range, right? Your friend can hear you, but your friend that is over there cannot hear you. And the reason why, because when you are talking, the intensity of your sound over there, it is not big enough for that person or for that friend to be able to hear that one, yeah? So of course now we're going to start with the wave intensity. So what is wave intensity? We can say wave intensity is basically the time rate of what? Of the energy flow, you can say, through a unit area, of course, which is perpendicular to the direction of wave travel. What do I mean by this? We can say this, remember, so wave intensity, all right, wave intensity is what? It is the time rate, you can say, of energy, yeah? So we can say wave intensity, I for intensity, remember this. All right, so equals to what? Equals to the energy or change in energy divided by change in time, of course, divided by the area. So we can say it is the time rate of the energy, you can say, that throws per unit, let's say, or through the area, which is perpendicular to the direction of wave travel. So remember this, but we said that sound, propagates in 3D or 3 dimensions. So this area is going to be the surface area of a sphere, not a circle, because if it is a circle, we know that that is basically pi r squared. But if we're talking about the surface area of a sphere, and of course that is 4 pi r squared. So this is what we have, all right, which is the surface area for a sphere. So I can rewrite this equation as this. I can say intensity or wave intensity of a sound equals to what? Equals to delta, or change in energy, of course, divided by delta time, divided by 4 pi r squared, okay? But we've already learned that, all right, that delta energy, all right, or delta E over delta T equals to what? Equals to power. So can I rewrite this equation, and instead of saying energy divided by time divided by the area, can I say power by the divided by 4 pi r squared? Yes, so this is basically the two equations that we're going to use for what? For the intensity of a sound wave, you can say. All right, so now this is the intensity, yes? All right, so what about the unit of intensity? Now take a look. Based on this or this equation here, we can say the unit of intensity equals to what? What is the unit of energy? That is joules, yeah? The unit for time, that is basically second. What about the unit for area, or just radius squared? That is going to be meter squared. So we can say the unit for intensity is joule per second divided by meter squared. But you do know that, can I rewrite, let's say this, right? Can I rewrite joule per second like this? Joule multiplied by 1 over second. That is also possible. I can write it this way as well. So let me erase this one. We can say I think I should have kept it this way. All right, let's keep it this way for now. So joule per second, yeah? And then, of course, divided by this. I can also rewrite this one here. Joule times 1 over second multiplied by, divided by meter squared. Why am I doing this? Because you've already learned that 1 divided by second equals to what? Isn't that equals to hertz? Yeah, basically, or frequency. Because for frequency, remember this equals to 1 over period, or 1 over time, that is 1 over second. So 1 over second, that is going to be in what? Equal to hertz. So I can rewrite the equation here. I can say joule hertz divided by what? Divided by meter per second squared. By the way, I can simplify joule furthermore, all right? Let's say we've learned that joules equal to what? All right, joules is a unit of energy, and of course, energy here would represent the work done, you could say. So we can say, or instead of rewriting this one, let's just simplify this furthermore, yeah? We can say joule is basically, right, is a unit of what? A unit of work done. So work done equals to force times distance. That is basically Newton, or measured in Newton, and that is measured in meters. So I can rewrite this one. I can say, instead of joule, I'll write Newton meter, and of course I can take the second back and then divide it by meter squared. But Newton also equals to, that is a unit of force equal to mass times acceleration, yeah? So instead of Newton here, I'll write kilogram, that is for mass, because Newton, it comes from mass times acceleration. So mass is kilogram, acceleration, that is meter per second squared, yeah? Multiplied by this meter, and then divided by, of course, we have another second there, and divided by meter squared as well, yeah? So now I have 2 meters. You can see meter and a half second squared, and then multiply by this one as well. So after simplifying this, or you can say it becomes like this. Let me make it longer, one more step. So kilogram meter squared divided by second cubic, of course, divided by meter squared as well. So these 2 meter squares will cancel out, of course. Then what is left now? Of course, we can say the unit of intensity can also be kilogram over what? Over second cubic as well. Over what? Over second cubic as well, all right? Remember this, that is the simplest form of what? Of the unit of the intensity. All right, now, that is basically the unit of intensity. So it could be joule per second, it could be joule per second per meter squared, it could be joule hertz per meter squared, or it could be kilogram per second cubic as well. Now, what about this equation here? You do know that the unit of power is what? The unit of power, of course, it is watt, yeah? And of course, for meter squared, or the area is going to be meter squared as well. So we have another unit for intensity, which is watt per meter squared. And this one here, we can say this unit is the SI unit for what? For sound intensity. All right, so what are the units of intensity now that we have so far? It could be, once again, joule per second per meter squared, or it could be joule hertz per meter squared, or it could be kilogram per second cubic, or it could be watts per meter squared. Okay, now, so that is what we have basically. At the definition of wave intensity, you can say the time rate at which energy flows through a unit area perpendicular to the direction of wave motion, or we set delta E over delta T, that is power, yeah? So we can say wave intensity is basically equal to power per unit area. And take a look here. What does this figure represent or tell us here? Remember that this one, it tells us that intensity is directly proportional, or before that, okay, we can see here as you move further away from the source of the, let's say from the source of the sound or the wave here, you can see this energy that we have, it is going to distribute over a larger and larger and larger area. And if that is the case, that means the intensity is going to be less and less and less. And if you're very far from the source of the sound, that is unlikely you're going to, or you're not going to hear, let's say the sound. Not because the sound is, or the frequency of the sound is not in the audible range. It is in the audible range. Maybe you're just too far. The intensity of the sound is not big enough so that you can hear the sound. All right, so of course, here's, like the units that we just derived, you can say, and this is the unit that you're going to get to. Now, we have, remember this, it says, because we're using, or the sound propagates in 3D, you can say, so in a spherical wave, the energy propagates equally in all the directions here. So of course, it's not just a circle, that is for the sake of the area. So in this case, the power the power emitted by the source, that is P, is distributed over a spherical surface, you can say. So the area of a spherical surface is going to be 4 pi r squared, not just pi r squared, it's going to be 4 pi r squared. Now, we have another relation. So what is the intensity, let's say, or based on the equation that we just had, let's say, now we know that intensity is what? Okay, so based on this, we can say intensity of a sound is directly proportional to what? We can say intensity of a sound directly proportional, the first thing, let's say proportional to the amplitude square, or you can say the amplitude for now. Do you remember in the previous video lessons, we said that energy is directly, let's say proportional to what? To the amplitude square. You might say, but that is energy, yeah? What about the intensity? And of course, intensity equals to what? We just said intensity equals to delta E over delta T, that is divided by 4 pi r squared. Isn't this energy? So of course, if energy is directly proportional with, let's say, the square of the amplitude, that of course, it means that the intensity is also directly proportional to the amplitude squared here. That is one thing. Yeah. Another thing that we have where you can say the intensity is directly proportional to is the surface or the vibrating surface area, let's say. What do I mean by this? Let's say, if you have a ruler, yeah? So let's say you have a ruler, you can, let's say, move this ruler or put your finger, let's say, on the top of the ruler and let it vibrate, yeah? And of course, now this ruler is going to, let's say, bend a little, and of course, it moves back and forth, it vibrates, yeah? So the vibration that you get from this ruler is not very loud. So, but what happens if you put this ruler, let's say, on the edge of a table, let's say? In this case, of course, all right? In this case, let's say, here's a table, right? So this ruler is against the table. Now, if you, for example, let's say, plug the ruler now or just let it vibrate, you will see that this ruler is going to vibrate. And of course, it causes a way bigger sound. And why is that? That is because when this ruler is vibrating, of course, it is attached to what? To the table now. So part of the vibration is going to go to the table. Now, the table surface, or at least the part that is connected with the ruler, or part of that surface is going to vibrate with the ruler or because of the ruler. And of course, in this case, you can see that there is a bigger vibration. And of course, now a bigger area, or you can say more air molecules would be affected or vibrating. Of course, the surrounding air would be vibrating with the ruler and the table, so the sound of the vibration is going to be louder. In another word here, because the surface of the ruler and the table are both together, these are all vibrating, so it causes a louder sound here. That is what we mean here, by the way, okay? So the bigger the surface, the area, all right, the surface of the area that is vibrating, remember this because we have two areas, yeah? One of them is, let's say the other area is basically was this one here, yeah? So remember this one, that is different. This is the area that the sound can cover, the sound can travel through, yeah? But this one here, or this area is basically this one. It is the area that the sound is vibrating with, okay? So the bigger the area of vibration, not the bigger the area of sound travel, yeah? The bigger of the area that the surface vibrates, the louder the sound will be, or the intensity of the sound will be. So we can say another thing that the sound is directly proportional with is the surface area, or you can say the vibrating area. The vibrating area, right? Or area. So the bigger the area of vibration, we can say the bigger the sound intensity. And of course, another factor that is also directly proportional to the intensity of the sound, that is the power, all right? Also, power, because you can see here, this 2 equals to the power. So the bigger the power, the bigger the intensity, or the louder the sound, you can say. But one more thing about the vibrating area, I can give you this. Let's say if you have a string, just a string, if you pluck it once, you will see that the string will vibrate back and forth, and of course, maybe the sound is not that loud, of course, let's say, and it vibrates for, let's say, for too long, yeah? But what happens if you attach this or the same string with a guitar, let's say? And of course, in this case, because the string is attached to the guitar, when the string vibrates, the guitar's body vibrate with it, so of course you will hear a louder sound. But remember this sound is going to be, like the vibration of the string will be way shorter. Why? Because part of the energy of the vibration, or let's say if the vibration will transfer to the body of the guitar, so now the whole body, the string and the whole body of the guitar is vibrating, or at least let's say the box of the guitar would be vibrating with it. So now there is a bigger vibration. Of course, that means you can see the energy of the string will be more efficiently transferred to the air through the string, through the body of the guitar. So we will hear a louder sound here, okay? But of course, the vibration is going to be shorter because this energy, of course, is going to the air way quicker than before. So now we can say intensity is directly proportional to what? To the amplitude. It is directly proportional to the vibrating surface area, or surface, let's say area. And of course, intensity is directly proportional to the power as well. But one more thing, you have to be aware of this. The intensity is inversely proportional with what? The intensity is inversely proportional with the radius squared. It's not just the radius, it is the radius squared. That means if we double the distance here, let's say here's a person who's talking, okay? So let's say the distance is 1 meter, and of course there is another observer that can hear this, yeah? And of course the intensity that the person hears it is, let's say, that a certain intensity. What happens if this person, let's say, increases or goes further apart? Now this distance, let's say, between the person who's speaking and the other person becomes 2 meters, yeah? In this case, the intensity of the sound will be reduced by a factor of 1/4, you can say, yeah? So in this case, we can say the intensity here, let's say we increase the distance, yeah? Whenever they give you intensity and distance, or let's say if the distance increased to this much or decreased to this much, what will happen to the intensity, yeah? So you can always use the equation here, yeah? So we said the distance doubles. If the distance doubles, what will happen to the intensity? You just use the equation. So we know that intensity is inversely proportional to the radius squared. So in this case, 2 squared in this case, we can say the intensity, all right, will be less, or will change by a factor of 1/4, yeah? Now, okay, what if we change the situation, let's say? Let's say we have a certain intensity of, let's say, at what distance will the intensity, let's say, increase or decrease, let's say, by a factor of, let's say, 2 or 3. Let me give you another example here. At a certain distance, yeah? Let's say at a certain distance we have the intensity. At a certain distance, the intensity of a sound, let's say it is, let's just say it is, okay. You give me a number. Let's say it is 5, let's just say, yeah? All right. At what distance, let's say, no, not this question here. Let's say at what, yes, I think it will be best if I say this. At what distance will the intensity of a sound will be reduced by, let's say, 5, let's just say, yeah? At what distance the intensity of a sound will be reduced by what? By 5. Okay, so basically we're seeking, or we want the distance here. We're saying at what distance will the intensity be reduced by what? As a matter of fact, let's say by 1/5. I think it would be best if we say 1/5, yeah? All right, so now all they have to do, just use the equation that we have just used, yeah? So let's say intensity, we said it is directly or inversely proportional with 1/r², yeah? So now remember this, that all you have to do, just like plug the numbers into the equation. So basically we want to find r, so we'll say r², it is, you can say, inversely proportional with what? With the intensity here. So what is the intensity? The intensity is basically, it is 1/5. So 1/1/5, of course the 5 goes up here, so we can say r², it is directly proportional now with what? With 5 in this case. But we don't want r², we want r, yeah? So in this case, of course, we'll take the square root for both sides. We can say, so r becomes the, or you can say it is directly proportional with what? Or the value that we're looking for is basically the square root of 5 here. So we can say when the r increases by a factor of the square root of 5, the intensity will reduce by 1/5. So remember this is very important. Now there is one more thing we can do actually for this, and that is this. Let's say we're given let's say two distances, we want to find the relationship between the intensity and the distance. And of course, we can use this relation, yeah? We can say or we want to find the intensity of, let's say, the second intensity divided by I2 divided by I1 equals to what? Equals to, because these two are inversely proportional, so this one becomes R1 squared divided by what? Divided by R2 squared. So you can see that these two are opposite to one another. So when do we use this equation? Let's say if they gave us different distances, what will happen to the density? You will just plug in the numbers and then you can find either the ratio, let's say, or you can just cross multiply to see which one, for example, whether you want to find I2 or I1. But there is one more thing you need to be aware of. If they ever ask you to find the ratio, let's say, then of course in this case, whenever they say find the ratio of, let's say, the two sounds in this case, of course, in this case, it becomes I1. Don't forget, I1 over I2. And of course, remember, if these two are opposite, you can say, so if this is I1 here, R2 squared should be here. And of course, R1 squared should be here. So you just plug in the numbers, then you will find the ratio here. So if they didn't ask for the ratio, then you can use, of course, whether I2 over I1 or I1 over I2. It is up to you. But don't forget, it has to be the correct correlation between the two. All right, now going back to this, and these are the details that you need to know about this. All right, so intensity is directly proportional with the amplitude squared, with the vibrating area, with the power as well. And of course, these are directly proportional, but intensity is inversely proportional with the area, or more specifically, you can say with the radius squared here. All right, and of course, you can use these equations to find whatever that is needed. Now we have a study tip. The study tip says what? As the distance from the source increases, what do you think will happen to the intensity? The intensity of the sound decreases. And why is that? That is because the power of that sound remains constant, but because now this sound covers a larger area, so we can say this power will be distributed over a very large area. So in this case, the intensity, of course, will be reduced in this case, yeah? And of course, this will be the same as the example that I just gave you. Let's say two friends are talking here, and then there is a third friend which is far there, yeah? So when they're talking here, they can hear one another perfectly fine. But for the other person over there, they cannot hear them. Why? Because the power for this person who's speaking here or talking here will be distributed over a very large area, which is not enough, for example, for the other person to be able to hear that. And if we want the other person to hear that, if they're not too far, of course, then you can either talk louder or you can even shout to call their name, and then they can hear you. All right, take a look here. We have question 17 says what? Why is the intensity of an echo is less than the original, or the intensity of the original sound? Now this should be very easy for you to answer, and that is because, let's say here's a person talking. All right, so of course the sound goes all the way, let's say, to the wall, yeah? That is one way. And for the sound to come back, that is echo, yeah? So echo basically is the reflection of the sound, yeah? But remember this, for the sound to go, that is basically 1R, yeah? And of course, to come back, that is basically 2R, yeah? So of course, the echo travels a longer sound. This is one of the reasons why you can say the intensity will decrease, because we said intensity is inversely proportional with what? With 1 over the squared, R squared here. So the echo would cover a larger distance. A larger distance, that means low or less intensity. That is one reason. And another reason is this, because when waves strike a surface, the reflection is never, or you can say rarely, perfect, yeah? Or you can say there is always part of that energy will be absorbed by the wall. So for example, when you talk, of course, your sound will go and hit a wall, yeah? The wall, let's say, is going to reflect part of your sound. So what happened to the rest? Part of it would be, of course, absorbed by the wall. If the wall is not thick enough, of course, maybe part of it will be transmitted as well here. Okay, so basically we can say the distance increases, that is one, and of course because the wall is not a perfect reflector. These two reasons make the intensity of the echo to be less than the intensity of the original sound here. All right, so take a look here. We have some questions, or some Wizari national exam question. It says the time rate at which energy flows the time rate. Time rate, remember, which energy flows through a unit area perpendicular to the direction of the wave motion. That is what? That is basically the definition of sound or wave intensity. Yeah? And that is basically, you can say, can we say wavelength? That is not. Can we say wave speed? That is also not. Wave intensity, that is the correct answer. What about wave frequency? That is incorrect. So the correct answer, of course, it is option C here. Now take a look at the second question. It says, if the distance from a point of a source of a sound, it is tripled. What does tripled means? That means the distance increases by a factor of 3 here. So by what factor does the sound intensity change? Yeah? So questions like this, remember, yeah, we said you just have to write the equation and then of course you can find what it is. So remember this with me, yeah? So we have intensity, it is inversely proportional with the radius squared. So here intensity, it is, we can say inversely proportional with the distance is what? It is triple. So of course 3, that means increased by 3 times. So of course now 3 squared, we can say that the intensity in this case of course will decrease by a factor of 1/9. So this is going to be the correct option here. Now take a look at the third one. It says what? If the distance from a point source of a sound is doubled, yeah, by what factor is the sound intensity change? If it is double, that is 1/r squared. So double, that means 2, yeah. So 1/2 squared, that is becomes 1/4. That is also option A here. Now take a look at question 4 here. That is a bit interesting. It says the change of sound intensity of a source. The change of sound intensity of a source by a factor of 1/3, yeah? Or to change the sound intensity by 1/3, the distance from the source must be changed by what factor here? Now this is interesting. So remember, we want the sound intensity to change by what? To change by 1/3. So by what factor should we increase or decrease the let's say the distance here? So we said, once again, write the equation. So 1/r squared. Now we want to find r, so you can plug in the numbers here and then find r, or it would be best if you just switch their places. So r squared, you can say it is inversely proportional with the intensity. So r squared inversely with what? With 1/3, because it says the intensity of I, we want to change by 1/3. So 1/1/3, so this is r squared. So we can say r squared, it is, now in this case, this 3 goes up, we can say it is directly proportional with what? With 3 here. But we don't want, let's say, the r squared, we want r, yeah? So in this case, of course, we're going to take the square root for both sides here, so this 2 will cancel out. So r must be changed by a factor of what? By a factor of the square root of 3 here. All right, so do we have this option in the answer? Yes, so here's the correct one there. Now there is another one here. There is another way you can say this. Intensity, it is inversely proportional with 1/what? With 1/r squared. Now, in order to get 1/3, that is what we want to change, yeah, the intensity with. So which one of these numbers should I plug, let's say, into the equation? I'll get 1/3. And of course, that is, let's say, the square root of 3, yeah? So square root of 3, that is squared, yeah? So these 2 will cancel out. So the intensity in this case is going to be what? The intensity will change by a factor of, let's say, of 1/3. But it would be best if you use the other method, okay? Since it is easier to comprehend. All right, question 5 says spherical wave intensity, that is the equation of wave intensity, which is, of course, power over 4 pi r squared. Which of the following is the unit of sound intensity? Remember, sound intensity, we said it is equal to, or the SI unit for sound intensity was watts over meter squared. Now, take a look at this one. Question 7 says, what is the ratio of a sound intensity at a distance of 4 meters to the intensity of a sound to a distance of 2 meters here? Now, I want you to pay attention here. It says, what is the ratio? We said if there is ratio mentioned, what is the equation that we use? Of course, we said I1 over I2, right, equals to, remember, these 2 has to be opposite. So R2 squared over R1 squared, yeah? So that is one way. Or another way you can say this, yeah? So how do we know it is I1 over I2? It says, what is the ratio of sound intensity at 4? So we can say this is I1, yeah? Very good. So at a distance of 4 meters, that would be the intensity at 4 meters, yeah? Then to the intensity of sound at a distance of 2 meters, so that is going to be I2 here. So I1 over I2, but remember, because these 2 are inversely proportional, So it's going to be R2 on the other side of the fraction. Let's say R2 squared over R1 squared, because these are inversely proportional with one another. All right, so here now we're going to what? We're going to plug in the numbers here. So the second distance, it is 2, yeah? So it's going to be 2 squared. The first distance that we have for R1 is going to be 4, yeah? But that is 4 squared, yeah? So the answer is going to be 4 over 16, yeah? If you simplify, this is going to be 1 over 4. So the answer is going to be A in this case. So it is not 1 over 16, it is not 4. If you flip this one here, of course, if you're going to use, let's say, R2 over R1, perhaps you're going to get this one here, but this is going to be incorrect in this case. So the correct answer is going to be 1 over 4 here. All right. Now, sample problem 4a. What does it say? It says, what is the intensity of a sound? So find I, intensity of a sound. All right. Find what? Find the intensity of a sound. Right? I of a sound. Sound wave produced by a trumpet at a distance of what? Of 3.5 meters. That is the R, the distance, yeah? When the power output of the trumpet is 20 watts. So we have power as well. It says assume that the sound waves are spherical. So that is easy enough. So write the equation of, or use the equation of the intensity that has power in it. So we can say intensity equals to power over what? Over 4 pi r squared here. So what is the power? The power is 20 watts, okay, divided by 4 pi. What is the radius that is, or the distance that is 3.2? But don't forget it is squared, so you divide the two, and then of course you will get 0.16 watts per meter squared. All right, take a look at this one. This is again very similar to the previous one. At a maximum level of loudness, the power output of 75 pieces. Let me make a pause on this one a little. So let's say, I can zoom out a little bit. Okay, so take a look here. It says what? All right, so at a maximum level of loudness, the power output of 75 pieces orchestra radiated as sound is 70 watts. So we have, you can say, the number of devices, or the devices that we have, basically 75, yeah? So how many devices do we have? We have 75 devices, okay? So we can say N, or the number of devices. Come on, let's take this one back. All right, so we have N, let's say, which is 75 devices, okay? And then it says the power of all this, it is basically 70 watts, okay? And then what is the intensity of a sound? Find the intensity, all right? It says what at a, let's say, of these sound waves to a listener who is sitting 25 meters from the orchestra. So in this case, we can say R is 25. So how do you find the intensity? We can say, of course, intensity equals to what? Equals to, yes, power over 4 pi r squared. So what is the power? 70. Divided by 4 pi, what is the distance? The distance is basically 25 squared. So once you divide the two, you will find the intensity, which is going to be 8.91 times 10 to the power negative 3. That is watts per meter squared. That is the intensity of sound. But hey, listen, this basically the intensity of 75, let's say, devices, or you can say pieces of orchestra, yeah? What if the question we're asking, what is the intensity of one piece, yeah? In this case, that is the intensity of 75, yeah? You would just divide this one by 75, you will find the intensity of one piece. What if they were asking for the intensity of 2 pieces, or 10 pieces, or 20 pieces? Then you'll still divide by 75 to find the intensity of one, then you would multiply by 10, 20, or whatever the numbers of devices that they would be asking you. All right, take a look at this one here. That is also very similar to the previous one. So just the application of the equation. But here, what they want to is find the power. Yeah, so power equals to what? I can just let's say tell you how it is done. We know that intensity equals to power over what? Over 4 pi r squared. So we want the power. So rearrange the equation. Power equals to intensity times what? 4 pi r squared. Plug in the numbers, of course, you'll find the power. Don't forget it is measured in watts. All right, moving on to this one here. This is the same as the previous one. You're given, it says a stereo speaker right, represented by P here, okay? And in the figure on the right, emits a sound wave with a power output. So we have power, which is 100 watts. What is the intensity of a sound at a point X where R is 10 meters? So we have power, we have R. You can find the intensity using this equation. These are pretty basic. All right, now let's talk about the intensity and frequency, all right? Or we can say intensity and frequency determines what? Determines which sounds are audible. So we can ask a question. Is frequency the only thing? Do you remember in the previous video lessons we said the frequency or the average frequency for human, or the audible range of frequencies for human, lies between 20 hertz to 20,000 hertz, yeah? But do you think every single sound in this range will be heard by, let's say, by people? The answer is no. And why is that? Aren't these frequencies or audible? They can be heard? Yes, that is true. But what if you're talking and let's say somebody's very, very far that are talking to you? Do you hear them? No, even though the sound they are talking or speaking with, let's say, has a frequency that is in the audible range, but because they are too far, all right, the intensity of the sound that is received by you is very weak, or you can say very small, that doesn't help you to hear what they are saying. So we can say there are factors that affect the audibility of humans, right? What are the factors that affect our hearing, or let's say our hearings depend on? And these factors are the frequency and of course the intensity as well. All right, which means that we can hear frequencies if they are at a certain intensity. If not, we will not be able to hear them. Okay, so the frequency of a sound wave heard by an average human range, of course, that is what we said. It lies or ranges between 20 to 20,000 hertz. We did talk about this one. The intensity is also a factor. Remember this. So the intensity is also a factor where we can hear sounds with frequencies that lies between these, let's say, 20 to 20,000 hertz. So in another word, if the frequency is not high enough or big enough, then we will not be able to hear the sound, even if its frequency lies between 20 to 20,000 hertz. Now, so we can say, what does the audibility of the average human ear depends on? Of course, it depends on both frequency and the intensity of that sound. So take a look at this picture here. We have a graph, of course, you can see. All right, take a look. What does it represent? Of course, we have, normally when you're given a graph, always look at the axis. Of course, on x-axis, we have frequency. On y-axis, we have intensity. Yeah? So look at what we have. Of course, we have basically these regions represent different regions of, let's say, sounds, let's say. By the way, these are all areas of sound, of course, you can say, but this is the area of sound, this is the area of, let's say, speech region. When we talk to, let's say, to our friends, or let's say to somebody that is in the room, that is the region that we are talking with. And of course, this region, you can say, it is kind of like, it is frequency range from, let's say, 100 to what? To sort of like something like 7,500 or something close to that, yeah? That is the area of speech region. Of course, we have a bigger region than that. That is music region, yeah? As you can see here, the frequency has a bigger, you can say, bigger region, yeah? But then, of course, there is two more things that are, or you can say, and of course, there is air of sound as well. There are two things that are near to you, and that is the threshold or threshold of hearing, and of course, threshold of pain. What are these things, okay? Now, threshold of hearing, that is basically the point where you start to hear sounds, or in another word, you can say this is the softest sound that you can hear. So what is the softest sound that you can hear? The softest sound that you can hear, of course, it lies, or it kind of like, it is where when the frequency is about 1,000 here, and of course the intensity is about, let's say, 1 times 10 to the power negative 12 watts per meter square, then of course this is going to be the softest sound that you can hear. The softest sound that you can hear is called the threshold of hearing, the point where you start to hear, okay? And of course, if, let's say, the frequencies were higher and the intensities were higher, then of course you can hear normally, yeah? And of course you can see, by the way, we can normally, or if I say something different here, take a look at this graph here. We can say for those sounds, that would be a second point actually, for these, all right? But let me go ahead and tell you this. For sounds that are, let's say, lower or with frequencies that are lower than 50, and of course for sounds that are, let's say, with frequencies that are, let's say, higher than 12,000, of course, or something here, then of course these sound has to be at a certain intensity so that we can hear them. Otherwise, we will not be able to hear them. So sound at low frequencies below 50 hertz, and also we can say those that are above 12,000, let's say 12,000 hertz, must be relatively intense to be heard. So once again, if a sound has a frequency that is, let's say, less than 50 or higher than 12,000 hertz, then those sounds has to be intense, all right, so that we can hear them. Otherwise, we will not be able to hear them. So sounds with frequencies less than 50, or you can say sounds of frequencies bigger than 12,000. So the intensity has to be big enough so that we can hear them. Otherwise, we don't hear them. What about sounds in between this? Yeah, and of course, any sound in between this, that'll be in the speech region. You can say we can hear them normally fine, even if they are at low intensity. Take a look at point number 5. Says what? Sounds in the middle of the spectrum are audible even at lower frequencies. That is going to be, you can say, speech region here. All right, sounds, or you can say the softest sound that can be heard, remember, by the average human ear, it is basically occurs at a frequency of about what? Of about 1,000 hertz, and of course at intensity of 1 times 10 to the power what? To the power negative 12. So we can say the softest sound that we can hear has about 1,000 hertz, and of course the intensity of about 1 times 10 to the power negative 12. But remember this is for average human, let's say, beings, yeah? And of course there are some other people that can hear sounds, let's say, with smaller, or you can say with lower intensities than that as well. But for this one here, the softest sound at 1,000 hertz at an intensity of 10 to the power negative 12, that is basically the softest sound that can be heard by average human being, and that is called threshold of hearing, okay? All right, and then, but remember this, we said that is for the average, yeah? There are some exceptions. There are some human beings, of course, you can say, can hear slightly softer sounds, okay? So at frequencies of about 3,300 hertz as well. So we can say, all right, there are some other people that can, you can see this point here, that is about 3,300 hertz. Of course, you can say this, or this sound can be heard even though the intensity is lower than 10 to the power negative 12 watts per meter square. Yes, so the loudest sound that human ear can hear, all right, can tolerate without getting pain, that is called what? That is called threshold of pain, and it is intensity is about what? It is about 10 or 1 times 10 to the power negative 10 to the power 1 times 10 to the power 0, all right, then that is basically 1, we can say. All right, so I'm going to summarize this one for you in a second, yeah? So exposure to sounds above the threshold of pain, of course, it will cause immediate damage, even if pain is not felt, all right? Remember this. We're talking about the intensity, or the, let's say, the highest intensity of a sound that can be heard by human without getting or feeling pain, that is, we can say 1 watts, or the intensity is basically just 1 watts per meter squared. If sounds were louder, we can still hear them, but you instantly feel pain. Even if you don't feel pain, they will instantly, let's say, cause a damage to your ears. And now, prolonged exposure of sounds of lower intensities can also damage the ear. It's just not the sounds with high intensity or big intensity, let's say, high intensity, that can cause damage, all right? Sounds with low intensity can also damage your ears if you are exposed to these sounds for a very long time. And this is one of the reasons why you see musicians or bands of the, let's say, or these bands, of course, they wear earplugs too, so that they don't hear the sound for too long, yeah? Or so that they can protect their ears, yeah? So why? We have a question, point 11 says, why many musicians wear earplugs during their performance? That is because prolonged exposure to sounds, even of lower intensity, can cause damage to their ears. That is why. So they're trying to protect their ears. Now we have two definitions: threshold of hearing, threshold of pain. Threshold of hearing, it is basically the softest sounds that can be heard by what? By average human beings, which occurs at a frequency of 1000 and an intensity of about 1 times 10 to the power negative 12. Threshold of pain, the loudest sound that a human being can tolerate without getting pain. It is or you can say have an intensity of about 1 watts per meter squared. All right, so let me emphasize or summarize this real quick. Yeah, let's say our audibility range or our audibility is determined by 2 factors: by frequency and by the intensity. So even if you have the right frequency, but if the intensity is not enough, you might not hear the sound. That's this. Threshold of hearing, that is the softest sound that you can hear, which is about 1 times 10 to the power negative 12. Threshold of pain, that is the loudest sound you can hear without feeling the pain, that is about 1 watt, or the intensity of 1 watts per meter squared. And then other frequencies, of course, you can say can be heard normally, okay? And of course, there are some other people that can hear sounds even softer than, let's say, 1 times 10 to the power negative 12, but the frequency has to be about 3,300 hertz, yeah? And these are all you need to know about this one. Make sure you go through these points one more time so that you will understand better. Next time, we'll start from relative intensity, or you can say relative intensity is measured in joules. So till then, keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullahi wa barakatuh.